Oh, sorry, I didn't see you there. So what brings you in today? So you're wondering a little bit about basic atomic structure? All right, I think I can help you out with that. How about I'll get some things ready here, and while I'm doing that, you can go ahead, get something to write with and something to write on. Now, through our discussion of atomic structure, the questions that we're going to try to answer will be, what are atoms? What are atoms made of? And what are the different ways that atoms can be different from each other? Now, the definition of an atom is that it's the smallest piece of an element that can still have the same chemical properties of that element. So for example, the smallest piece of carbon that you could have would be one atom of carbon. The smallest piece of lead that you could have would be one atom of lead. Once you split that sample up more, you're splitting it up into different types of atoms or subatomic particles, the things that make up the atom. The things that make up atoms are called subatomic particles. Subatomic means smaller than atoms. And the three that we'll learn about are called protons, neutrons, and electrons. These each have abbreviations that can be used in diagrams or equations. Proton will be a lowercase p with a plus sign after in the upper right. Neutron is a lowercase n with a 0 in the upper right, and electron is a lowercase e with a negative sign in the upper right. The proton and neutron each have a mass of what's referred to as one atomic unit. It's a very, very, very small mass. And so to talk about individual atoms, they talk about a proton and a neutron approximately being equal to 1 in terms of their mass. The mass of an electron is about 1/2000th of an AMU, and so they're really contributing just about 0 mass to an atom, and they're typically just counted as 0 mass. So one atomic mass unit is 1.66 times 10 to the negative 24 grams, or 0.00023 zeros and then 166 grams. Where these are located within an atom, the protons and neutrons are centered in the nucleus of the atom, the middle of the atom. The electrons orbit the nucleus. You can see that based on their notation that protons have a positive electric charge, electrons have a negative electric charge, and neutrons have no charge. When we talk about charge, we talk about how they would interact with an electric field or a magnetic field. And so protons with a positive charge are attracted to negative parts of magnets or electromagnetic fields, and electrons are attracted to positive sides of magnets and electromagnetic fields. In a typical model of an atom, let's say helium, we'll talk about how to figure this out in a moment, but a helium atom, just to think about the size of these, a helium atom has in its nucleus 2 protons and 2 neutrons. And orbiting its nucleus, it has 2 electrons. And you can draw a picture of it like this, but this is drastically out of scale. These things are so small that an atom is really mostly empty space. If you were to replace each of those protons and neutrons in a helium atom with BBs, the electrons are so small compared to them, they would be like the smallest grain of chalk that you could obtain. And so if we were trying to think about how big this atom would be with our nucleus of protons and neutrons and our electrons orbiting, the scale of this, the diameter of a single proton is 1.68 femtometers, which is 1.68 times 10 to the negative 15th, while the diameter of a helium atom is 62 picometers, which is 62 times 10 to the negative 12 meters. Now it's hard to imagine, because those numbers are so small, how drastically large that is. But what it's saying is, if this were actually what a proton size would be, that this tiny grain, this electron, would be orbiting about 1.5 football fields away. So if this were the size of the helium nucleus, the entire helium atom, where its electrons would be orbiting the nucleus, would be 1.8 football fields wide. So if I wanted to place this electron correctly, I would have to go outside and place it about 0.9, or almost a full football field, to the right, and it would orbit all the way around an entire football field to the left, and it would be orbiting so fast that it would appear to be a sphere that was that size with the nucleus in the middle. But I just wanted you to get an idea about how small these things really are, and that atoms, though we draw them and they look kind of full, they're mostly empty space. An atomic symbol is a way to represent all of the information about the subatomic particles that are contained within a specific atom. This is an example of an atomic symbol. It's got letters and numbers in the upper left corner, the lower left corner, and the upper right corner. The letters are what are called the element symbol, and those are from the periodic table. And so Ca, that means that this would be describing an atom of calcium. The number here is called the atomic number. The atomic number represents the number of protons, which in turn represents what element it is. So atomic number and element symbol really tell you the same information. If you know the element symbol, you know which element it is, and you know its number of protons, and you know its atomic number. So sometimes this atomic number is not included in the lower left, because if you have the element symbol, this is redundant information. You should be able to look at calcium on the periodic table and find its atomic number is 20, which is redundant. Every time a symbol here would be Ca, the number in the lower left would have to be 20. In the upper left is the atomic mass of that atom. And recall that the subatomic particles are protons, neutrons, and electrons, and of those, only protons and neutrons contribute to the mass. Electrons have pretty much a zero mass. Really, you would need 2,000 electrons to equal just one proton or neutron, and so the atomic mass is representing how many total protons and neutrons are in that atom. The last number in the upper right is the charge of that atom. And the two things within an atom, the two subatomic particles that have charge, are protons and electrons. And so the charge represents what balance of protons versus electrons there are. Recall that protons are positive and electrons are negative, and so a positive charge means that there are more protons than electrons by the number stated. If you see only a plus sign, that will mean 1 plus, that there are 1 more proton than electrons. And if you just see a minus sign, that means 1 minus, that there would be 1 more electron than proton. If you see no number indicated here, it either means that the atom is neutral, or you might see a 0, which means neutral, or it means that the charge of that atom is not important to that problem. So through this example, through these numbers, we can figure out the number of protons, neutrons, and electrons. Because this is calcium, it has to have 20 protons. You can check that on the periodic table. This is redundant information. The atomic number also would tell us 20 protons. To figure out the number of neutrons, you know that the total mass of the atom is 42. So that means that 42 represents the protons and neutrons added together. So to get the number of neutrons, you would take the mass number and subtract the number of protons. So I'll get out a calculator for that. And I find that the number of neutrons here is 22. For the number of electrons, you can see that the charge is 2 plus, and so that means that there are more protons than electrons, and so that means there are fewer than 20 electrons, and that there are 2 fewer. So again, I'll use my calculator, and I find that the number of electrons is 18. When you hear people talk about ions, what they're referring to are atoms that have an overall charge. They can have an overall charge if their balance of protons and electrons is not even. And so that means that they have either gained or lost an electron compared to their neutral form. It's always electrons that they would gain or lose. It's not that they would gain or lose protons, because protons are in the nucleus. And if there is a change to the nucleus, a reaction that happens in the nucleus, that is called a nuclear reaction. Chemical reactions typically involve just changes to electrons in atoms. Ions are called 2 different things based on if they are positively or negatively charged, whether they have gained or lost electrons compared to their neutral form. They are named because of cathodes and anodes in batteries. A cation, just like a cathode on a battery, has a positive charge. And it has a positive charge because it has lost electrons compared to its neutral form. An anion is the opposite. It's a negatively charged ion and has more electrons than protons. A neutral atom is not an ion, but as a reminder, a neutral atom has the same number of electrons and protons. And there are various reasons why a cation or an anion might form if they have gained or lost electrons compared to their neutral form. Those terms for gaining and losing electrons are oxidation or reduction. And oxidation is when something has lost electrons and it becomes a cation, whereas a reduction is where something has gained electrons and become more negative, an anion. So ions are different ways that atoms can be different from each other based on their number of electrons. If atoms have different numbers of protons, then we say that they are different elements. So different protons means that they are different elements. Different numbers of electrons means they might be different ions. And so the other thing that might make different atoms different from each other would be number of neutrons, and that brings us to our last term, isotopes. Now, isotope is a relative term. You would say that two atoms are isotopes of each other if they have the same number of protons but differ in their mass number, which means a different number of neutrons. And so, for example, these are two isotopes of calcium. One has a mass number of 40, one has a mass number of 42. Because they are both calcium, they both have 20 protons. Because they have different mass numbers, they have different numbers of neutrons. When you're talking about different isotopes, you typically will be focusing on the mass number, and the charge is not listed because it is not relevant to these types of problems. Now, not all combinations of protons and neutrons are stable. There are isotopes where their combination of protons and neutrons make them unstable, and they would break apart, or they would give off protons and neutrons through a nuclear reaction. Remember, these things are in the nucleus. This is a chart that shows if the nucleus will be stable, or if it's a naturally occurring radioactive isotope, meaning that it breaks apart into other things and gives off radiation. And then these hollow boxes are artificially produced radioisotopes, meaning that they are radioactive and they are produced in a lab or in an atom smash or a particle collider. So you can see stable nuclei are black. The way that you would read this table, that you have number of protons on the x-axis, and so this represents what element it is. On the y-axis, you have number of neutrons. And so for the two isotopes I used in the previous example, to find where calcium would be, it has 20 protons, its atomic number. So this dotted line represents all of the calcium isotopes that are possible. So you can see this one is black, that's calcium with 20 protons and 20 neutrons, and that would be, this box represents calcium 40, since its mass total is 40. This hollow box below it represents calcium 19, which according to the key is an artificially produced radioactive isotope. Above it, another hollow box for calcium 21, a artificially produced radioactive isotope. But then we get to calcium 22, 23, 24, 26, and 28 are all stable isotopes of calcium. When they say stable, they mean relatively stable. They may still be slightly radioactive and decay over time and occur in nature in different percentages, but they are relatively stable. The concept of percent abundance really talks about that although there were a number of stable calcium isotopes, in nature some of them are more rare than others. So if you scoop up a sample of calcium, it will have a certain percent of isotopes that are calcium 42 and a certain percent that are calcium 40. I should note, because I'm speaking about them, that these symbols are written this way, but if you were to write them in paragraph form, they would be referred to as calcium-40 and calcium-42. This is not a minus sign, they're a dash, and they are representing the isotopes where this is the mass number. And so, for example, we'll look at the different isotopes of calcium since I was referring to them before. These are the naturally occurring isotopes of calcium. And on a reference chart, you can see that they do not occur equally in nature, but that of all the calcium atoms that you would find in nature, that 96.9% of them are calcium 40. And the other percentages are as follows. These are all rounded, so they may not add up exactly to 100%, and this isn't exactly 0, it's 0.004%. Now, what we have on the periodic table, though, is only one mass listed for calcium, and it says 40.078. And what is on the periodic table is an average atomic mass. And what's on the periodic table is they're talking about an average atom of calcium. And that doesn't really seem like it would work out if what's listed on the periodic table is 40.078, because 40 plus 42 plus 43 plus 44 plus 46 plus 48 divided by 6, the number of isotopes, would give you 48.3. And so the average atomic mass really takes into account these percentages. It's called a weighted average, where instead of just a straight average of the different mass numbers of the different isotopes, it weights them by their percent. And so what it does is it would take 40 and then multiply by its percent, and then add 42 times its percent abundance, and then add 43 times its percent abundance, and 44 and 46 and 48 times their percent abundance. And so to calculate the average atomic mass, it's the sum of each product, where you take the mass of that isotope times its percent abundance, and you would add up all of those together, and you would get the average atomic mass. Take care that when you do this, that your percents are in decimal form, and so instead of saying 40 times 96.9, you would say 40 times 0.969, 42 times 0.006. Because this is a percent, you would move the decimal place 2 places over to represent that percent as a decimal. And you would get what is on the periodic table, 40.078. Now, percent abundance and average atomic mass are interesting because different samples of calcium from different places in the world might have slightly different percentages, and that will let you track where that sample of calcium came from. So you can tell from an archaeological dig, if you look at the calcium in the bones or in the teeth, you can look at the percentages of different isotopes of calcium, and you can tell a lot about where the calcium in that person's diet came from. It's called forensic or anthropological isotope analysis. You can also tell how old different things are by their percent of different isotopes of elements. So for instance, you can look at the ratio of carbon 14 which is a radioactive form of carbon that we are ingesting while we are alive. When we die, or when fossils start forming, their percent of carbon-14 goes down relative to carbon-12. And so analyzing that percent, you can tell how old something is. So you can analyze percent abundance of different isotopes of an element, not only to determine where on Earth, or if it came from space, where that sample came from. You can also determine how old that sample is based on different percent abundances of certain isotopes. So that's it. Hopefully now you can understand what atoms are, what they're made of, and how different atoms can be different from each other, whether they have a different number of protons, making them a different element, whether they have a different number of electrons, which means they could be neutral or a positive or negative ion, or if they have different number of neutrons, which means that they would be isotopes of each other. So if you need more practice, you can get questions answered in class when you come in. And as always, stay positive and test negative.